So let's have a look at practical 10, which is to make a solid organic product, something like aspirin or something of that nature, and to purify it via recrystallization and then to test its purity using a melting point. So let's have a look at practical 10, specimen 2015 version 0.5, specimen 0.5, and it's question number 9.2. Doesn't really matter what the steps are from before. We're recrystallizing a product, a solid. It's dissolved in a minimum quantity of water. Solution is filtered to get rid of this filtration, removed any insoluble impurities. The flask was left to cool, and then the crystals were formed, filtered off, compressed in the funnel. A little cold water was then poured through the crystals, and the crystals removed, reweighed, and a small sample was then used to find the melting point. Okay, so what do you do? So you've made this aspirin, you've filtered it, so you've got it in your filter funnel, but it's not very pure, it's crude. So you dissolve it in a minimum amount of hot ethanol, or in this case it says hot water. The aspirin dissolves, the impurities don't. So you filter off the impurities, and the aspirin that's dissolved in the hot water or the hot ethanol, whichever solvent you've decided to use, comes through into the bottom of the conical flask when you filter it using reduced pressure filtration. Then, because you've used the minimum amount of hot ethanol or hot water, if you cool the solvent down, then less aspirin can dissolve. So some of it recrystallizes, i.e. no longer can dissolve in the solution. The impurities are in the filter paper at the top. The purified aspirin now is in the conical flask at the bottom once you've cooled it and it's recrystallized, and then you can filter off the pure aspirin. Dry it, because the main impurity is water, test its melting point. If you get a melting point close to the actual melting point, it's pure. The closer it is to the real melting point, the purer it is. Also, the colour would give you an indication, the whiter it is, and also if it melts at a sharp melting point. If it melts very quickly, sharply, rather than over a range, it's also pure. So let's try and answer this. Why is the minimum quantity of water used? Hot water, so that when you cool the water down, the crystals would reform or recrystallize. Why was the flask cooled? Well, the cooler it is, then the less aspirin can dissolve, and you'll get a bigger yield. So cool it down to give a bigger yield, or I suppose the other way around, you can say if it's warm, it's going to give a lower yield. The crystals were compressed in the funnel, so that's so the air comes through the actual crystals rather than around the outside, and it's going to help dry it. And why was little cold water passed over the crystals at the end? That's to wash away any insoluble impurities. The melting point in the sample was found to be slightly lower than data put value, suggests the most likely impurity. It's always water, and the best way to get rid of water is to press the crystals through some filter paper to try and absorb the water. Let's carry on then. Let's go to June 2020. Question 4. It's given you a method to make aspirin, and it's missed out step 4. So you've added some salicylic acid in a weighing boat, which is like a small dish, ceramic dish or glass dish. Place the weighing boat on the 2 decimal place balance and record the mass. Tip the salicylic acid into a 100 centimetre cube conical flask. And part 4 is that you're going to have to re-weigh the empty weighing boat, because you want to work out how much salicylic acid you've added, and you can't assume that it's all gone from the weighing boat. There might be some still left in the weighing boat that you've not tipped into the conical flask. So that was part 4, so that you could then calculate by subtraction the exact mass of salicylic acid that was added. The mass that you've got at the beginning, take away the mass that you've got any left in the boat, at the end is the mass that's gone into the conical flask. Suggest a suitable piece of apparatus to measure out the ethanoic anhydride. That's a liquid, so you could use a measuring cylinder. It says add 10 centimetre cube of ethanoic anhydride, or a pipette or a burette, or a measuring cylinder, a 10 centimetre cube measuring cylinder. You've got to try and think that rather than just put measuring cylinder, put a 10 centimetre cube measuring cylinder, because that's going to be easier and more accurate to measure out 10 centimetre cube rather than, say, for example, a really big one like a 100 centimetre cube measuring cylinder. A corrosive is a hazard of using concentrated acid. So they've used something called concentrated phosphoric acid in the reaction. You've used concentrated sulfuric acid when you've made aspirin, and you know that it's corrosive. It will burn your skin. Suggest two ways in which the melting point of the crude aspirin collected would differ from melting point of pure aspirin. Well, the cruder it is, or the less pure it is, the lower the melting point. Another difference would be it doesn't melt at a sharp temperature. So pure aspirin would melt at a sharp temperature over a range of temperatures. You could also look at its appearance as well, and have a look what it looked like. And if it was white, it's likely to be more likely to be aspirin. Precautions when heating up ethanol: use a water bath. Don't use a Bunsen burner, because ethanol is flammable, and you know that you've got to use the minimum volume of ethanol when you're dissolving and recrystallizing. Otherwise, it won't come back out of solution. It won't recrystallize. Why do you add a small amount of cold ethanol? That was to wash away any soluble impurities at the end. One other difference you'd expect to see, and we already mentioned, is appearance. Pure aspirin is likely to be whiter or paler in colour. Or you could say it's got larger crystals. The larger the crystals, when it recrystallises, it forms larger crystals. But I think whiter in colour is your most obvious answer there.